All right, so video about kinetic energy, which closes out this unit, right, over energy, well, kinetic energy, I should say, and momentum. Okay. Energy, as you can imagine, there's many different forms. You kind of talked about that. Kinetic energy, in a physics sense, right, is all about motion. And, this one is perhaps the easiest one to visualize, right? When something moves quickly, when something heavy moves quickly, you're like, that's got to take a lot of energy, right? And in your day to day life, you've probably noticed this. If I said, go run a marathon, you're like, that's going to take a lot of energy. Well, because you have mass and you're trying to move along the marathon course, right? 26.2 miles. Even thinking about running that right now sounds scary to me. And if I told you what would make it harder, you might say, well, if I had to run it faster, like, yeah, it takes more energy if you're moving quicker, right? More velocity takes more energy. Okay, you can kind of picture that. You're like sprinting a marathon. That ain't gonna happen. I don't care if you're the best marathon runner in the world. You ain't sprinting that. That's just not gonna happen. Okay, you're gonna jog it basically, and maybe your jog speed is higher than someone else's, right? I mean, that's how you win the marathon. But yeah, you're not going full speed. Usain Bolt, right? He's, I believe, still the fastest person ever, right, in terms of running speed. He's not going to win a marathon. Why? His body is built, like he's trained himself to run short distance, okay? And he's very fast at that. But if he ran a marathon at that speed, it's not going to happen. Okay, he's going to tire out way before. I mean, probably way before even a mile he's going to tire out, right? Okay, but if you imagine trying to run that speed, it would take a ton of energy. How else can I make it hard for you? If I said, hey, wear this backpack full of bricks, you'd be like, no, I don't want to do that because it's increasing your mass. It's making it basically heavier, which means you have to move that mass. You need energy to cause that mass to move, and to keep that mass moving, you need energy. Okay, so hopefully when you, when you think of kinetic energy, hopefully you're thinking about this. You're like, okay, motion takes energy to keep us going, right? If we're in outer space, it's different. There's no forces acting on us. But on Earth, we have air resistance, we have gravity, things we have to fight. So I need all this energy to keep myself moving. Okay, hopefully that's making sense. When we think about energy, again, fundamentally, energy at its core is the capacity to do work. And work basically means to cause something to change. For motion, it's obvious. Moving a ball takes energy. Yay. We just talked about that. Toasting bread takes energy, right? You need heat. Well, the heat, there's a couple things going on here, is causing the molecules inside the complex mixture that is bread to speed up. And that speeding up causes basically some chemical reactions. One of them is a dehydration, which pulls the water out of toast. That's why toast gets crispy. Toast gets black because the sugars and the sugars, the fiber, various carbohydrates in general, right, to lose the water that is basically, for lack of a better word, embedded in their molecules. It's called a dehydration. Toast gets drier, and toast also gets black because a lot of the chemical reaction is causing other things to leave, which leaves behind carbon, which is why if you toast bread for too long, it turns black because you basically turn it into carbon. And it doesn't taste very good anymore, right? Because the sugars and whatnot are missing, and it's not going to taste like bread anymore. Okay, but you're causing things to change. It takes energy. Okay, simplest at a simple level, that's what's going on. Okay, and again, examples here: pushing, pulling, dragging. Right, you get the idea. Heating an object, cooling an object, causing something to change. Generally speaking, takes energy. Okay, and again, we focus on kinetic energy. All right, movement. Kinos is the Greek word. I think I'm pronouncing it right. I don't know. Anybody who speaks Greek can make fun of me and say, no, that's not how you pronounce it. But it means motion in Greek, right? That's where kinetic energy comes from. Okay. The equation, we like equations. Equations are great. Is this right here? KE equals 1/2 mv squared. Okay. KE, I don't really like that this is often written like this because it looks like two variables, K times E, which to me, I'd be like some constant times energy, but it's commonly written this way. I wouldn't panic too much about it, especially for like a freshman level physical science class. I wouldn't panic about this. Okay, KE, kinetic energy in joules. Okay, joules is the measure. A joule is a measure of energy. It's also a measure of work because work and energy are basically the same thing. Okay, M is mass in kilograms. We've seen this a lot. Hopefully you're like, yep, I know that one. And then of course V for velocity. and velocity is given in meters per second. Can't stress enough, make sure it's the right unit. If it's not the right unit, it will be wrong, okay? Are there ways you could rewrite this equation to be given in grams and maybe kilometers per hour? You could, okay, but that's not what we're doing, all right? And I'm not saying you can't do that. I'm just saying it's why make your life more complicated right now. Okay, you take physics, then we do more complicated problems, and then you got to learn how to do that. But we're not there yet. Okay, nothing wrong with that. So what does a problem look like? I could have maybe this, a 16 kilogram ball is traveling at, 100 meters per second, and I want to find the amount of energy it takes, or how much the ball has, essentially. I would take my mass, take my velocity, plug them into my equation. So 1/2, which, by the way, you could write as 0.5, right? A half is the same thing as 0.5. Mathematically, they're the same, right? So whether you multiply by 1/2 or by 0.5, it's the same thing. Times the mass, 16 kilograms, times, notice I have parentheses around the velocity, okay? And we're squaring it. You might say, okay, sure, why do I care? Because if I have a negative velocity and I square it, I better get a positive number. And if you're like, why is that? A negative times a negative is a positive, always, okay? We're not going to talk about complex numbers. We're going to stick with rational numbers. Always going to be negative times negative is a positive. Okay, so if you square a negative, you get a positive. In a lot of calculators, and this is a big pet peeve of mine, so any mathematicians listening to this video could be like, well, actually, and I can be like, no, I don't like it. When you square a negative in a calculator, so if you say -5 squared without parentheses, most calculators interpret that as -1 times 5 squared, which gives you what? -25. And that is not -5 squared, is it? Right? That's -1 times 5 squared. But you typed it in -5 squared. So why would the calculator anyway? What does it mean for you? Put it in parentheses. So if it was a negative velocity, if it was say -10, -10 in parentheses squared. And that way you get the right answer. Okay? Because energy cannot be negative. A change in energy can be negative, but not an energy by itself. Okay, energy is not a vector. Okay. All right, and if you're saying, what does that mean? It means it can't be negative. All right, another one, right? Your favorite DJ Khalid. I think is how you pronounce it. I don't know. I never even checked. I don't listen. I know what the guy looks like. I don't know. I know what his voice sounds like. Never heard his name, actually. Not a fan of his music. Anyway, how much energy would it take to get a 1,000 kilogram boulder to a velocity of 1.2 meters per second? Again, list out your variables, plug in your numbers into your equation, and we get a simple answer, right? 1/2 times 1,000 times 1.2 squared. And what does that give us? 720 joules. Okay, I guess I should have given the answer to the last question. I kind of skipped that, didn't I? 80,000 joules. Right, for this, I just realized, I'm like, wait a second. For this one, 720 joules. Okay, hopefully not that bad. This was, I think this is a very important thing, I think. Okay, again, every teacher has their opinions. In my opinion, as a science teacher, when you learn equations, you should be thinking about what variables matter. Obviously, the ones listed, but are they all treated evenly? Are they the same? As in, like velocity and mass, if I put them both in, do they both have an effect on energy? And of course, the answer is yes. But the question is, are some more important than others? And in this equation, the answer is absolutely yes. Velocity is way more important. Okay, and why is that? Well, simple. You see in the equation, let me jump back here, right? In the equation, we have a half. That doesn't change. That's a constant, right? We have m. M is just m. You plug in 10 kilograms, you plug in 20 kilograms. Kinetic energy goes up, right? If I plug in, 10 for mass, 10 kilograms, and then I double it to 20, Ke doubles. And if you're like, I don't know, prove it to me. I don't think you're telling the truth. I think you're trying to pull a fast one on me. I'll pull up Desmos. Desmos is a great tool for visualizing math, which I think is very helpful. So if I have my kinetic energy, let's call this E for energy. It is equal to 0.5, which is a half, times m times v squared. And I can, in Desmos, I can have these little sliders, which is pretty useful. Okay, so right now I have, let's do 10, right? So energy would equal to 5 joules. If I double this, so times it by 2, now the energy has gone up from 5 to 10. And you're like, well, yeah, I mean, I doubled it. Shouldn't it double? Yeah. What if I make it 5 times bigger? Hey, it's 5 times bigger. Oh, okay. That's because it's linear. Okay, it's linear, which means if I double it, it doubles. If I triple it, it triples. If I half it, right, if I cut this in half, right, you can see energy gets cut in half. And you're like, okay, yeah, obvious. Because it's linear, because it's just m. But if I look at v, you're going, hey, that's squared. Yes. And so now if I double velocity, look what happens to energy. So I'm going to double it. It went up to 20. Well, that's not 10. That's not double. That's more. As a matter of fact, that's 4 times bigger. Okay. What if I make it 3 times bigger? So I'm going to multiply this by 3. Now it's 45, which is 9 times bigger. What if I do 5 times bigger? Now it's 125, which is 25 times bigger. And hopefully by now you're noticing a pattern. Let's do the last one, which hopefully really sells you on this. If I make it 10 times bigger, now it's 500, which is 100 times bigger. Okay? And the pattern is that velocity has a quadratic relationship with kinetic energy, which simply means if I double it, it is 2 to the second power bigger because it's being squared, which means 2 times makes it 4 times bigger. If I make it 3 times bigger, 3 squared is 9. It's 9 times bigger. If I make it 5 times bigger, 5 squared is 25, and so on and so forth. So what all this means, going back to the slides, is that velocity is way more important than mass. I'm not saying mass doesn't matter. I'm not trying to say mass has no impact. That's not at all what I'm saying. I'm just saying if you had to pick which one's more important, velocity by far, okay? And again, this skill I'm trying to teach you is not just for this equation. It's any equation you see. You want to ask yourself, well, what if I change it by the, if I change mass, if I change velocity, if I change energy, if I change this, how does it affect everything else? Right? If you're thinking like a scientist, you're trying to understand the relationship of these variables. And sometimes it's just, oh, double it, it doubles. And sometimes it's, oh, no, there's a big, big, big difference. Okay. Give you a little example here. If you look up what's called beam deflection, so I'll just show you this, like a little example here. So if I type in beam deflection, you say, what is beam deflection? There are a lot of calculations. Let me get out of here. That we can do in structural engineering that talks about how strong basically a material is. Like a hair in my mouth. Anyway, talks about how strong a material is. This is the equation. Oh, I guess it's like size -1 font, it feels like. This right here, I don't know if you can see, it says PL to the third over 48 E to I. And you say, I don't know what that means. It basically means if I had a beam, like a metal beam in like a building, right, that's supporting the building, it's preventing it from collapsing, how much weight can I put in the middle, and how much does that cause it to bend, right? So, if it's made of wood, right, if you step on a 2x4, it bends in the middle, right, assuming you have 2 supports, right? This is how much will it bend. That's what this equation is. And you say, oh, okay. And hopefully you're saying to me, oh, L to the third, L must be really important. And you'd be right. L is the length of the span, the length between the 2 supports. And it has a cubic relationship, which means, okay, you say square, that's important. Cubic is even more important. Cubic means for every time you double it, you get not only 4 times bigger, you get 8 times more deflection. If I make it 10 times longer, it means 1,000 times more sag, 1,000 times more deflection, right, which is basically bending in the material. So again, when you learn this, not that you don't need to know this for this, right? I'm not going to give you beam deflection questions in this class, but hopefully you're saying, oh, I understand. Like we should be looking at these and not just saying they're numbers and letters, thinking what the relationship is between variables. Okay, I value that because I want you to be a scientist, not just doing calculations. Okay. All right. What else? Yep, got that. Cool. Last bit then is about potential energy and kinetic energy. The notion here is, you probably learned this at some point before. I don't make a huge deal about it. To me, it's kind of an whatever thing. I'm not saying it doesn't matter. I just don't. I think it's pretty straightforward. Basically stored energy. Okay. And when you learn about this with kinetic energy, you should be thinking about potential energy as, does it have the ability to get faster? Because remember, velocity has a very big impact on energy. So, the classic thing you're taught is you put something on, I don't know, this is a bookshelf, and you say there's not much potential energy. Well, there is because it's above the ground, right? But my hand's in the way. If I take it away, it falls. It accelerates because gravity is causing it to accelerate. It gets faster, which means it gets more energy. Okay? If I make the distance bigger and bigger and bigger, it has more time to accelerate, which means it has more velocity, which means it has more energy. That is how you should think about potential energy. Okay? When people teach it as just higher means more, okay, why? You should be saying why. Okay, like if you're scientifically minded, and you might say, "Oh, that's not me." No, it is you. You just gotta dig in and say, "Yeah, I can figure this out." Okay, if you just live life saying, "I guess," there's nothing wrong with that. But again, you can uncover a lot more if you're curious and want to learn how things work. So when you learn something, scientists were like toddlers. We're always saying, "Why? Why? 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 Why?" We don't learn why. Okay, so you learn this, you hear, oh, it goes higher, it's more energy. You say, why? Well, it has more time to accelerate, which means it has more velocity, which means it has higher energy. Okay, so that's how you should think about this. All right, if you look at a common, easy way, or not easy, but a common way of visualizing this is that if I put energy in to make something go higher up, it's almost like charging a battery because now it has time to accelerate and get faster and faster and faster. Okay. Potential energy is not free. You don't just get it. You gotta charge it. You gotta get it ready. It's like a spring. You gotta compress the spring that takes energy, right? You're storing energy. Same thing here. By me picking something up, I need to put energy in to move it up, and then when I'm ready to let go, then it falls back down. I'm releasing it. That is one way you could picture this potential energy idea. Okay. So that's pretty much it. Hopefully it all makes sense. Hopefully you're saying, oh, okay. Hopefully you're not saying, oh, good, the video's over. Hopefully not. Anyway, have a great rest of your day. Enjoy and see you later.